So let's start the first part of our code. So we create a class LSTM, and we want to start with an init. And the input of the init is the number of neurons / the number of states. We will not want to have the x vector xt in the init, and there's a reason for that, and I will show you later. So we will use xt as an input for the forward part. However, what we can do already is if we know how many states we want to have, that we set up all the learnables or pre-allocate matrices for the learnables. And we want to do this with random numbers, of course. And as we learned in just 1 or 2 slides earlier, that, for example, the size of UF is just n neurons times 1. And this is the part that you can change if you want to have more than one feature LSTM. Then this number, of course, is not 1. It's just the number of features you have in your data and you want to have in your LSTM. Then, of course, and we have the same structure for the forget gate, and of course, as we have for the input gate, and we also have this for the output gate, and of course for the part we called z tilde. So we just need to set up, in principle, just one learnable, and then just to copy and paste and just continue with that. And then after the init, we will create our forward part. So let's first of all create our init, and therefore let me just move back to my user interface to Spider, and let's set up the code. And I have the RNN from the last lecture where we can copy and paste a few things. But again, if you don't have it, just feel free to copy and paste or download it from my GitHub repository. So let me just first of all create the class. So we probably are gonna need we need NumPy, and therefore we wanna import NumPy, of course, and then let's set up our LSTM. And also here, I wanna save this in our work folder as before. So we have a work folder, LSTM, and I want to save this under one LSTM cell. So 1 stands for chapter 1, and also navigate to this folder. So therefore, let's create the init. And the input is just the number of states or the number of neurons. And we also want to save this, of course. Let me just copy and paste. All right, and then we want to set up or pre-allocate the matrices for the learnables, and we want to do this with random numbers. So we just start with some values, and as we learned earlier in the other lectures, so practically it by experience it works the best if we have normally distributed random numbers with not a very large dynamic range. So we want to multiply this with 0.1, and then of course we need the size of the matrix or the shape of the matrix. So it's the number of neurons or states times 1. Again, we want to have one feature LSTM. So let's start with the forget gate. And we want to do this for UF, for BF, and also for WF. Be careful here, the size or the shape is n times n. And let's do the same thing now for the input gate. So we just copy and paste that. and change the index. Maybe I should have a capital W here because I also used it in the slides. Then we want to do the same thing for the output gate. So we can just say that's O. And then finally, so that's our class here. And finally, we want to also do this for, what I called C tilde. So we still have the same structure, so we can just copy and paste this part of the code. All right. So let me just compile it. So we have our init, and now we want to add the forward part. And in the forward part, the input is xt. So when we have our xt here, this is our input. And there's a reason why we don't want to have it as an input in the init. We want to have it in the forward part, and you will see later why. So what is supposed to be in the forward part? So let me just go back to our to the PowerPoint. So in the forward part, first of all, we need to know the length of the vector xt, and we want to remember that. So we put in the self and also xt itself, and then based on this, we want to set up lists, and those lists contain vectors for h, c, and c tilde, because we want to keep track of the states h and c, and also of c tilde. And we want to do the same thing for the numbers that are generated in the forget gate and the output gate and also in the input gate. So actually, we don't really need to do that. However, if, for example, there's something wrong in the output or we get an error message, it really helps to look at those vectors or those states in order to find the reason or the bug why the code doesn't really work. And anyways, just for investigating what the LSTM does, it's pretty helpful to look at those values. So again, we don't need F, O, and I, but just in case that we want to fix some errors or want to fix some bugs, then it makes sense to have these values. So therefore, let's go back to our user interface. So we have xt, and now let's first of all determine the length of xt, which is the number of time steps. And let me just check where there's an, oh yeah. So let me just check whether the indents are. Okay, so then we want to also self this. And then we also save xt. And want to keep the code neat, so that's why I rearrange it here. But then also we want to recover the number of neurons that we have here, because we need it now for setting up those lists. Okay, so what is the first list? So we want to create a list for age. So this is the state vector, and we have a certain number of states, which is the number of neurons. So we can pre-allocate this with n0 of np zeros, and this has the size number of neurons times 1. And we want to do that for every time step t, so that we have all these states for every time step t. And we have an initial value h, we pass it on to the cell, and it always generates an output value h. So that's the reason why we have always one more. So that's the reason why the range goes to t plus 1. And we had this case already in the RNN. So we have h that we start with an initial value, then we put it into the cell for the first time step, and then for the last time step, it's also generating an output h. And this is also true for C. So we can just copy and paste that. That's not true for C tilde. For C tilde, we have as many values, so to say, or as many vectors as time points. All right, and then we want to keep track of all these values that have been generated in the different gates. So for example, the forget gate. So we can also just copy and paste here because we have as many values as time points t. And as we discussed in a few slides ago, the shape is number of states or number of neurons times 1. So we do this with the forget gate. We do this with the output gate. And we're also going to do this for the input gate. So let me just save that. And there's one more thing, actually two more things. So first of all, we want to change those values, those learnables, using our optimizer. And therefore, we also need to calculate those changes, and we always denoted them with D. So we also have to set up or pre-allocate matrices, which have the same shape as the learnables, but always with the D to make clear this refers to the change to the derivatives, because that's what we want to use then for the gradient descent method, where we add this to our current values, and they will be calculated through the backpropagation. So we want to do this with all the learnables, not only with the forget gate. We also want to do this with the input gate, with the output gate, and also what I called C tilde. So in principle, we can just go to our code and just copy and paste what we did for the learnables themselves, but always add a D. So let me just go back to the code again. So we can just copy and paste this part here. And just add a D. But be careful, don't forget the D, because otherwise you would reset the learnables every time. And of course, we don't want to do that. So in the forward part, of course, for every epoch, we are calculating these values again, and then we add them to the learnables. So that's the reason why we have the learnables only in the init part, but the changes of the learnables we have in the forward part. We could in principle also put them here, and then they will be overwritten all the time. But here we can just reset them because then we make sure for every epoch we have a new value that we have just calculated from the backpropagation. Okay, so now we have initialized all the matrices, and there's one more thing that we need, and let me show that. So we have initialized all those matrices, but of course we also need the activation functions like the sigmoid and the tangents hyperbolicus. And we want to create lists with different instances for every time point that we create for every time but an instance. Because what is the idea? Of course, for every time step, we create an output, and then we want to run the backpropagation through time. So once we have one epoch throughout the different time steps, then we have, and if we want to do the backpropagation through time, then we always have to multiply the outer derivatives with the inner derivatives of those activation functions. And of course, for every time step, we will have a different value. And that's why I want to create a list with all the different instances, because all these different instances will then have the inner derivatives. And we just need to multiply these inner derivatives with the outer derivatives. So in the same way we did with all the other lectures. That's why we want to have these different instances. And we, of course, want to do the same for the tangents hyperbolicus. And now we can also just copy and paste those activation functions from previous lectures. So let me just go back to our code again. So the first thing that we need is the tangents hyperbolicus for from our RNN, for example. So again, if you don't have it from the previous lectures, you can just copy and paste it from the GitHub repository. So then we have the tangents hyperbolicus, but let me just quickly save this here. Of course, we want to save this as LSTM in our work folder. So let's save this as LSTM. And we need the tangents hyperbolicus. And we also need the sigmoid. And also here, we can just go to earlier lectures, for example. Or again, just go through, download it from the GitHub repository. So we have our activation functions and we have our sigmoid. So we just copy and paste that, or you download this, and then we have the different activation functions. So we have the sigmoid layer and we have the tangents hyperbolicus. And so there's already the forward part and there's the backward part. And remember how the backward part always worked. So we have the d values. These are the outer derivatives, so which come from the layer below the current one. And we have to multiply this with the inner derivatives. So here are the inner derivatives, and then here's the multiplication. And the inner derivatives, of course, always depend on the inputs. That's what you have here as well. And for every time t, those values are of course different. And that's the reason why we need these different instances. So one instance for every time step. So therefore, let's now go to our LSTM here, and let's set up all these different instances. So we set up an instance for the sigmoid, for the forget gate, for t in range t. And we want to do this for all the other sigmoids. So we have a sigmoid in the forget gate, we have one in the input gate, and we have one in the output gate. And now we want to do the same for the tangents. So we have two tangents. So let's call it just tangent hyperbolicus 1 and 2. Because we have 2 in our LSTM cell. So also here we can just copy and paste. And that's it. So also let us check whether it's been recognized. So we have it here as class with the forward and the backward part. So most of the work is already done. So most of the work has been done in the earlier lectures. And now we just need to put all those things together. All right, what else do we need for the forward part? So we have the activation functions. And of course, then as in the RNN, or in the example where we had the RNN, we set up a cell in the forward part. So the RNN cell in this case, in the same way we want to set up an LSTM cell. And we start at certain values from these particular vectors, HT and ZT. And these are the values for the time point 0, of course. And then we call a cell that we have to create first. And we have lots of input and lots of output. Most of the things are actually not necessary for run the LSTM itself. But we want to keep this output for the same reason that we want to record all the states and also keep track of all these values of the output, input, and forget gate. So just in case something goes wrong or there's something we don't understand, we can take a look at those values. And that's the reason why we have so many input and output arguments. I know it looks like a mess, but it really is really helpful if you have some bugs and need to fix some bugs and figure them out. So this is the cell, and this LSTM cell is performing the calculations for every time step in a single epoch. So therefore, it starts with these initial values HT and CT and fills up those values or creates values over the different time steps T and saves them in the corresponding matrices like H and C. And then we do the same thing, of course, for the forget gate, for the output gate and the input gate, and also C tilde. And then we want to save those values and also the instances. So that's the next thing we have to do. So we have to create our LSTM cell, which performs these calculations for every time step, and then we call the cell in our forward part. And every time in each epoch, we call this particular cell. And this is what we're going to do in the next chapter.